5. Computer organization. Foundations of computer science. 8. Disengaged learning. Objectives. After studying this chapter, the student should be able to list the 3 subsystems of a computer. Describe the role of the central processing unit, CPU. Describe the fetch, decode, execute phases of a cycle. Describe the main memory and its addressing space. Define the input/output subsystem. Understand the interconnection of subsystems. Describe different methods of input/output addressing. Distinguish the 2 major trends in the design of computers. Understand how computer throughput can be improved using pipelining and parallel processing. Input/output subsystem. We can divide the parts that make up a computer into 3 broad categories or subsystem: the central processing unit, CPU, the main memory and the input/output subsystem. Figure 5.1 Computer hardware, subsystems. 5:1 Central processing unit. The central processing unit, CPU, performs operations on data. In most architectures it has 3 parts: an arithmetic logic unit, A-LU, a control unit and a set of registers, fast storage locations. The arithmetic logic unit, ALU. The central processing unit, CPU, performs operations on data. In most architectures it has 3 parts: an arithmetic logic unit, A-LU, a control unit and a set of registers, fast storage locations. Figure 5.2. Figure 5.2 Central processing unit, CPU. Registers. Registers are fast standalone storage locations that hold data temporarily. Multiple registers are needed to facilitate the operation of the CPU. Some of these registers are shown in Figure 5.2. Data registers. Instruction register. Program counter. The control unit. The third part of any CPU is the control unit. The control unit controls the operation of each subsystem. Controlling is achieved through signals sent from the control unit to other subsystems. 5:2 Main memory. Main memory is the second major subsystem in a computer. Figure 5.3. It consists of a collection of storage locations, each with a unique identifier, called an address. Data is transferred to and from memory in groups of bits called words. A word can be a group of 8 bits, 16 bits, 32 bits or 64 bits, and growing. If the word is 8 bits, it is referred to as a byte. The term byte is so common in computer science that sometimes a 16-bit word is referred to as a 2-byte word, or a 32-bit word is referred to as a 4-byte word. Figure 5.3 Main memory. Address space. To access a word in memory requires an identifier. Although programmers use a name to identify a word, or a collection of words, at the hardware level each word is identified by an address. The total number of uniquely identifiable locations in memory is called the address space. For example, a memory with 64 kilobytes and a word size of 1 byte has an address space that ranges from 0 to 65,535. Memory addresses are defined using unsigned binary integers. Example 5.1. A computer has 32 megabytes of memory. How many bits are needed to address any single byte in memory? Solution. The memory address space is 32 megabytes, or 225, 25 times 220. This means that we need log 225, or 25 bits, to address each byte. Example 5.2. A computer has 128 megabytes of memory. Each word in this computer is 8 bytes. How many bits are needed to address any single word in memory? Solution. The memory address space is 128 megabytes, which means 227. However, each word is 23 bytes, which means that we have 224 words. This means that we need log 224, or 24 bits, to address each word. Memory types. 2 main types of memory exist, RAM and ROM. Random access memory, RAM. Static RAM, SRAM. Dynamic RAM, DRAM. Read-only memory, ROM. Programmable read-only memory, PROM. Erasable programmable read-only memory, EPROM. Electrically erasable programmable read-only memory, EPROM. Memory hierarchy. Computer users need a lot of memory, especially memory that is very fast and inexpensive. This demand is not always possible to satisfy. Very fast memory is usually not cheap. A compromise needs to be made. The solution is hierarchical levels of memory. Figure 5.4 Memory Hierarchy. Cache memory. Cache memory is faster than main memory, but slower than the CPU in its registers. Cache memory, which is normally small in size, is placed between the CPU and main memory, Figure 5.5. Figure 5.5 Cache memory. 5 to 3 input/output subsystem. The third major subsystem in a computer is a collection of devices referred to as the input/output, I/O, subsystem. This subsystem allows a computer to communicate with the outside world and to store programs and data even when the power is off. Input/output devices can be divided into two broad categories, non-storage and storage devices. Non-storage devices. Non-storage devices allow the CPU/memory to communicate with the outside world, but they cannot store information. Keyboard and monitor. Printer. Storage devices. Storage devices, although classified as I/O devices, can store large amounts of information to be retrieved at a later time. They are cheaper than main memory, and their contents are non-volatile, that is, not erased when the power is turned off. They are sometimes referred to as auxiliary storage devices. We can categorize them as either magnetic or optical. Figure 5.6 A magnetic disk. Figure 5.7 A magnetic tape. Figure 5.8 Creation and use of CD-ROMs. Figure 5.9 CD-ROM format. Figure 5.10 Making a CDR. Figure 5.11 Making a CDRW. Five to 4 Subsystem interconnection. The previous sections outline the characteristics of the three subsystems, CPU, main memory, and I/O, in a standalone computer. In this section, we explore how these three subsystems are interconnected. The interconnection plays an important role because information needs to be exchanged between the three subsystems. Connecting CPU and memory. The CPU and memory are normally connected by three groups of connections, each called a bus, data bus, address bus and control bus, Figure 5.12. Figure 5.12 Connecting CPU and memory using three buses. Connecting I/O devices. I/O devices cannot be connected directly to the buses that connect the CPU and memory, because the nature of I/O devices is different from the nature of CPU and memory. I/O devices are electromechanical, magnetic, or optical devices, whereas the CPU and memory are electronic devices. I/O devices also operate at a much slower speed than the CPU/memory. There is a need for some sort of intermediary to handle this difference. Input/output devices are therefore attached to the buses through input/output controllers or interfaces. There is one specific controller for each input/output device, Figure 5.13. Figure 5.13 Connecting I/O devices to the buses. Figure 5.14 SCSI controller. Figure 5.15 FireWire controller. Figure 5.16 USB controller. Addressing input/output devices. The CPU usually uses the same bus to read data from or write data to main memory and I/O device. The only difference is the instruction. If the instruction refers to a word in main memory, data transfer is between main memory and the CPU. If the instruction identifies an I/O device, Data transfer is between the I/O device and the CPU. There are two methods for handling the addressing of I/O devices: isolated I/O and memory mapped I/O. Figure 5.17 Isolated I/O addressing. Figure 5.18 Memory mapped I/O addressing. 5-to-5 Program execution. Today, general-purpose computers use a set of instructions called a program to process data. A computer executes the program to create output data from input data. Both the program and the data are stored in memory. At the end of this chapter we give some examples of how a hypothetical simple computer executes a program. Machine cycle. The CPU uses repeating machine cycles to execute instructions in the program, one by one, from beginning to end. A simplified cycle can consist of three phases: fetch, decode and execute. Figure 5.19. Figure 5.19 is steps of a cycle. Input/output operation. Commands are required to transfer data from I/O devices to the CPU and memory. Because I/O devices operate at much slower speeds than the CPU, the operation of the CPU must be somehow synchronized with the I/O devices. Three methods have been devised for this synchronization: programmed I/O, interrupt-driven I/O, and direct memory access, DMA. Programmed I/O, interrupt-driven I/O, direct memory access, DMA. Figure 5.20 Programmed I/O. Figure 5.21 Interrupt-driven I/O. Figure 5.22 DMA connection to the general bus. Figure 5.23 DMA input/output. 5 to 6 different architectures. The architecture and organization of computers has gone through many changes in recent decades. In this section we discuss some common architectures and organization that differ from the simple computer architecture we discussed earlier. CISC. CISC, pronounced CISC, stands for Complex Instruction Set Computer, CISC. The strategy behind CISC architectures is to have a large set of instructions, including complex ones. Programming CISC-based computers is easier than in other designs because there is a single instruction for both simple and complex tasks. Programmers, therefore, do not have to write a set of instructions to do a complex task. RISC. RISC, pronounced RISC, stands for Reduced Instruction Set Computer. The strategy behind RISC architecture is to have a small set of instructions that do a minimum number of simple operations. Complex instructions are simulated using a subset of simple instructions. Programming in RISC is more difficult and time-consuming than in the other design, because most of the complex instructions are simulated using simple instructions. Pipelining. We have learned that a computer uses three phases: fetch, decode and execute, for each instruction. In early computers, these three phases needed to be done in series for each instruction. In other words, instruction N needs to finish all of these phases before the instruction N+1 can start its own phases. Modern computers use a technique called pipelining to improve the throughput, the total number of instructions performed in each period of time. The idea is that if the control unit can do 2 or 3 of these phases simultaneously, the next instruction can start before the previous one is finished. Figure 5.24 Pipelining. Parallel processing. Traditionally a computer had a single control unit, a single arithmetic logic unit and a single memory unit. With the evolution in technology and the drop in the cost of computer hardware, today we can have a single computer with multiple control units, multiple arithmetic logic units and multiple memory units. This idea is referred to as parallel processing. Like pipelining, parallel processing can improve throughput. Figure 5.24 Taxonomy of computer organization. Figure 5.26 CISC organization. Figure 5.27 SIMD organization. Figure 5.28 MIST organization. Figure 5.29 MIMD organization. 5 to 7 Simple computer. To explain the architecture of computers as well as their instruction processing, we introduce a simple, unrealistic, computer, as shown in figure 5.30. Our simple computer has three components: CPU, memory and an input/output subsystem. Figure 5.30. The components of a simple computer. Instruction set. Our simple computer is capable of having a set of 16 instructions, although we are using only 14 of these instructions. Each computer instruction consists of two parts: the operation code, opcode, and the operand, S. The opcode specifies the type of operation to be performed on the operand, S. Each instruction consists of 16 bits divided into four 4-bit fields. The leftmost field contains the opcode and the other three fields contains the operand or address of operand, S, as shown in figure 5.31. Figure 5.31 Format and different instruction types. Processing the instructions. Our simple computer, like most computers, uses machine cycles. A cycle is made of three phases: fetch, decode and execute. During the fetch phase, the instruction whose address is determined by the PC is obtained from the memory and loaded into the IR. The PC is then incremented to point to the next instruction. During the decode phase, the instruction in IR is decoded and the required operands are fetched from the register or from memory. During the execute phase, the instruction is executed and the results are placed in the appropriate memory location or the register. Once the third phase is completed, the control unit starts the cycle again, but now the PC is pointing to the next instruction. The process continues until the CPU reaches a halt instruction. An example. Let us show how our simple computer can add two integers a and b and create the result of c. We assume that integers are in 2's complement format. Mathematically, we show this operation as: we assume that the first two integers are stored in memory locations, 4016 and 4116, and the result should be stored in memory location, 4216. To do the simple addition needs 5 instructions, as shown next. In the language of our simple computer, these 5 instructions are encoded as: storing program and data. We can store the 5-line program in memory starting from location 0016 to 0416. We already know that the data needs to be stored in memory locations 4016, 4116, and 4216. Cycles. Our computer uses 1 cycle per instruction. If we have a small program with 5 instructions, we need 5 cycles. We also know that each cycle is normally made up of 3 steps: fetch, decode, execute. Assume for the moment that we need to add 161 plus 254 equals 415. The numbers are shown in memory in hexadecimal as 00A116, 00F16, and 019F16. Figure 5.32 Status of Cycle 1. Figure 5.33 Status of Cycle 2. Figure 5.34 Status of Cycle 3. Figure 5.35 Status of Cycle 4. Figure 5.36 Status of Cycle 5. Another example. In the previous example we assumed that the 2 integers to be added were already in memory. We also assume that the result of addition will be held in memory. You may ask how we can store the 2 integers we want to add in memory, or how we use the result when it is stored in the memory. In a real situation, we enter the first 2 integers into memory using an input device such as keyboard, and we display the third integer through an output device such as a monitor. Getting data via an input device is normally called a read operation, while sending data to an output device is normally called a write operation. To make our previous program more practical, we need modify it as follows. In our computer we can simulate read and write operations using the load and store instruction. Furthermore, load and store read data input to the CPU and write data from the CPU. We need 2 instructions to read data into memory or write data out of memory. The read operation is. The write operation is. The input operation must always read data from an input device into memory. The output operation must always write data from memory to an output device.